Greetings, everybody. Learning is a hobby here. I want to continue with my problem of the day series. I know I took a little bit of a break. We got sort of a false start here on this playlist because I was on vacation. I explained all this already, so I'm not going to go through it again. But I want to start that back up again. So yeah, I'm gonna do uh, a problem that people are probably familiar with. This is a standard problem that you meet in like pre-calculus or even like an algebra 101 course, but I want to prove the theorem in four different ways just because I think it'll be interesting to see the four different methodologies. So let me bring up the problem. Okay, this is the problem. So what this theorem says is that for any natural number n, the sum of the first n natural numbers is given by this formula, n times n plus 1 over 2. There is a famous story about this formula involving Gauss, who, Carl Friedrich Gauss, who was one of the greatest mathematicians who ever lived, that when he was a young child in, his school, the teacher gave the class a problem to add the first 100 natural numbers together, as a sort of like a punishment, I guess, for misbehaving. And Gauss was able to do it immediately because he realized this formula was true. So you get 50-50, 5050 when you sum up the first 100 integers. Um, let's actually prove this the four different ways. I'll start with the way that I think. Actually, there's two ways that I think undergraduates usually are introduced to this formula. I'll do the one that's the most common, I think, first, which is a proof by induction. So I'll call this proof one. Right? So we'll induct on the natural number n. So here's our base step, right? The base step will be n equals 1. So if we take the sum, j going from 1 to 1 of j, that's just 1, right? And if you look at 1 times 1 plus 1 over 2, this is 2 over 2, which is also 1, so the base step is satisfied. Right, then we can go on to the inductive step, which, if you are familiar with mathematical induction, we always start by assuming the inductive hypothesis. So assume the formula holds for some natural number n. And then you consider this, you let n increase by 1, right? Take n plus 1 and see if the formula holds for n plus 1. So consider the sum j going from 1 to n plus 1 of j. Right now, I don't want to assume that it's equal to n plus 1 times n plus 2 over 2. That would be circular. So I want to use the inductive hypothesis to prove that the truth of the proposition sort of propagates through the successor function, right? So this is equal to n plus 1 plus j equal 1 to n j. And by inductive hypothesis, the sum that we have here is equal to n times n plus 1 over 2. Right? And then just combining like terms by putting everything over the least common denominator and factoring out the common factor of n plus 1 on top. Notice that this is n plus 1 times n plus 1 over 2. So the inductive step is satisfied. In other words, the formula holds for n plus 1 as well. And that proves that the formula works for all natural numbers by mathematical induction. So that's the proof. All right, that's proof number one. This is one that, like I said, is a standard proof that you see in every like undergraduate like algebra or recalculus course, if you if you know induction, sometimes colleges don't teach induction at that level. But if you've taken a proof class, this is a pretty common exercise to assign to the students. So that's one proof. Next one involves, so I'll call this proof two. Uh, Proof two exploits the fact that the sum is arithmetic. So what we can do is let Sn equal the sum, j going from 1 to n of j. This is 1 plus 2 plus 3 plus all the way up to n. That's what, the summation is shorthand for that long sum, right? Then what we do is let me just rewrite this so it's easier to see what I'm going to do. If I add another copy of Sn, but just with the order of the terms rearranged, this is n plus n minus 1 plus all the way up to 1, and I add these together, you get 2Sn on the left-hand side, and on the right-hand side, you get n plus n plus 1, all the way up to plus n plus 1. And notice that there are n of these. So this is n times n plus 1. And then to solve for Sn, you just divide by 2. Right? And that shows that the sum of the first n natural numbers is given by that formula. So that's another proof using the fact that the sum of the first n integers is an arithmetic sequence. Sorry, an arithmetic sum. Right? Then we can go to proof 3, which I guess you could call this sort of a more number theoretic proof. This involves the fact that the formula n times n plus 1 over 2 gives you the triangular numbers. So, for example, if you take the sum of the first n natural numbers, you can always arrange them in a triangular shape. So, for example, uh, say we have um, well, actually, let's do it like this. Let's actually construct it. So you have 1, and then 1 plus 2 gives you 3. 1 plus 2 plus 3 gives you 6, and so on like that. So, if you add 4, right? So 1 plus 2 plus 3 plus 4, right? You're adding all of these up. And then, if you go down to the nth step, you'll have n dots here, and you'll have a triangle shape. Okay, so then what we can do is we can actually take another copy of that sum. Let's call this, maybe we'll call it K. Call this K. Take another copy of that array of dots and, just write it up above here. So we're just taking another copy of that the dots in that triangle, right? Then we end up with, let's see how many dots. Here we have n plus 1 rows of dots, and here we have n columns of dots. So we have 2k dots, right? Because we took a copy of the k dots, right? And we have the number of dots in the rectangle there is n plus 1 times n, obviously, right? So n times n plus 1. And solving for k, we get n times n plus 1 over 2. And again, that shows that the sum of the first n integers is given by that formula. The values that you get by taking the nth term of a sequence with the using this formula are called the triangular numbers, by the way, because you can, like I said, you can always arrange them in a triangle. All right, and then lastly, proof number four um, occurred to me in bed last night while while I was trying to fall asleep. I'm sure that this is not, I'm not the only one that's thought of this. I'm sure this is a pretty standard thing, but this is a combinatorial proof, and I think it occurred to me just because I've been thinking a lot about the prime number theorem and getting bounds for pi of x, which is the function that counts the primes less than or equal to x, involves like a lot of combinatorial arguments. So I think my mind was just sort of primed to think about this. This is a combinatorial argument. So what we can do is consider the number of pair sets that can be formed from a set of cardinality n plus 1. Or actually, I'll use the integers just to make things a little bit easier to write down from the set 1 to all the way up to n plus 1. Okay. Um, so we can count these. So notice that we get the pair sets. Let's do actually cardinality of this. All right, the set of all pair sets that have one as an element um, involve, the all of the numbers in the set that are bigger than the other element of the pair set, right? Is has can only be one of the other elements in the set here, right? And there's n of those. So the cardinality of that set is n. And then if we look at the cardinality of the set where 2 is a one of the elements of the pair set and x is greater than 2, this has n minus 1, the cardinality of n minus 1. And hopefully, this makes sense if you think about it going down. The number of pair sets with n plus 1 as an entry, where x is greater than n plus 1. There's only one of those. And if you add all those cardinalities up, that gives you all of the pair sets, right? So I'll just say total number of pair sets is equal to 1 plus 2 plus 3 all the way up to n, right? I'm just adding up the cardinalities here, right? But we have a binomial coefficient that counts this as well. Also, the number of pair sets is given by the binomial coefficient n plus 1 choose 2. And using the formula for the binomial coefficient, this is n plus 1 factorial over 2 factorial times n plus 1 minus 2 factorial, which is n plus 1 times n times n minus 1 factorial divided by 2 factorial times n minus 1 factorial. And notice that the n minus 1 factorials cancel. So you end up with n times n plus 1 over 2. And that gives you a combinatorial proof for this formula. Okay, so again, just sort of a quick, easy one. I just wanted to show you the four different methods just because that combinatorial proof occurred to me last night. Like I said before, I was going off to dreamland. Just because I've had combinatorial proofs in my, rattling around my head because I've been thinking a lot about the prime number theorem. So let me know what you guys think down below. I'll see you in the next one. Hopefully, I'm going to try and keep these going, every day. So, every day have my problem of the day posted in the morning, and hopefully I can keep that up at least for a little while. I'll see you guys pretty soon.